So now we previously we have defined um, the moment of inertia is basically a sum of the mass times the distance from from the axis of this product. Okay, so let's do a thought experiment. For example, we have an apparatus here. It has a center shaft. It has two masses, right? If we want to easily rotate this object, then we need to reduce the moment of inertia. And in that case, we want to lock the two equal masses cylinder close to the center of the horizontal shaft, right? In this case, it would have a smaller moment of inertia and easy to start this apparatus rotating. On the other hand, we can actually increase the moment of inertia of this apparatus by lock the two equal mass cylinders far away from the center that go to the end. Um, and because of the moment of inertia is basically sum over all the mass time the distance from this axis, right? Ri here, Ri square, right? As we move this cylinder away from the rotating axis, then this whole quantity, basically the moment of inertia, increase. Okay. Right, so let's look at some of the real world examples. You can imagine a hummingbird that is very small, have very small mass, and also the size of the hummingbird is very small. So then it would have a very small moment of inertia. So the bird can move its wings very rapidly. So it can actually go as high as 70 beats per second. In contrast, if we have a large bird like this condor here, it has you know a wingspan of a couple meters, and the mass is also much larger than the hummingbird. So the moment of inertia of this bird is much greater than a hummingbird. So it can actually then it will be difficult for it to flap its wings very quickly. Typically, these birds are doing less than 1 beat per second. Okay, so this is basically real world examples where the concept of moment of inertia can be applied to. Okay, so now let's look at basically how to calculate the moment of inertia, right? In the original equation in defined here, so basically we're talking about all of these objects or particles are separated, right? So you basically do a discrete sum of the mass times the second power of the distance from the axis and add them up together, right? That gives you the total moment of inertia of the system. But the thing here is that for a continuous object, for example, this solid cylinder here, you wouldn't be able to actually do that discrete sum. And in this case, we basically are converting this Ri square time mi. We're basically doing converting this into a integral that will basically be r square dm, right? Okay, and the dm here would be the density at this point times the volume dv. Okay, that's basically this equation, right? That this term here, the row time dv, is basically dm and times the distance of this little volume, how far it is away from the axis. Okay, let's apply this equation to a solid disk or cylinder and calculate its momentum inertia as the axis actually travel through the center of this disk and is perpendicular to the top surface. Okay, so first of all, if the total mass of the cylinder is big M, the density would be the big M divided by the total volume of this disk. and that would be the mr squared times h, and the h is basically the thickness here, right? Okay, right. Mr squared would be the top surface area. Okay, right. That gives you volume. Then you can actually take a derivative of that d, and then here what is changing is the radius r. That will be 2 pi h r dr. Okay, and then we can plug that into this equation, right? Where we pull the rho out, because for this cylinder, we're assuming that this is a constant value everywhere. And basically we want to do this this integration where we put this here, right? Okay, that's here, right? And then we pull this constant out here, right? There's an error that this 2 pi r, this would be the big R, and you have basically r raised to the third power, and integrated over from 0 to r. That's the from 0 to the outer radius of this disk. Okay, then if you work out that math, and that would basically give you the total moment of inertia of this disk or the cylinder is half big M time the radius, the outer radius of this cylinder. Okay, right? That's basically how this is defined. Okay, how this is basically derived. This I equal to half mr squared is derived. Okay, so this is for a solid cylinder. What about the case we have a solid sphere? Okay, so you can think about, okay, the rotating axis is z-axis. Okay, and you can think about we basically can do is chop this sphere, a solid sphere, into a series of little disks, right? Here we can have an infinite series of little disks, right? For each disks, then the radius here is basically denoted by and how the radius here, if we um, uh, write it out as y, and how it is related to the z, and the outer radius of r is by this equation, right? This r squared, because this is a 90-degree triangle, so this y equal to r squared minus z squared. Z squared is how far this disk is away from the center of the sphere. Okay, so and that the y basically gives the radius of this disk. And then we look at the mass of this disk. dm of this one is would be the density time pi y square here, and time dz, that will be the short thickness here, that will be the dz here. And then because this is a disk, then we can calculate the momentum, the moment of inertia using this equation here, the half mr square, right? We have the half, we have the dm, we have the r square. Sorry, this one shouldn't be here, right? And then we put the dm term in here, right? That basically give you half time rho time pi time y to the fourth and dz. Okay, and the total moment of inertia of the whole sphere would be integrating all of these disks, the moment of inertia of all of these disks together. Then and here the y to the fourth power, we can basically plug this in. The y to the second power is r squared minus z squared here, right? And by integrating this out, that will give you a divided by 15 time the density time pi time the outer radius raised by the fifth power. Okay, so here's a short derivation that that you can go through to arrive at this answer. Basically, we expand this r squared minus z squared term, and that will give you basically this equation here. And of course, here, if we know that the total volume of this sphere is m, then its density will be big M divided by 4/3 of a pi times r to the third power, and then you will basically arrive at the 2 divided by 5 mr squared. That will be the moment of inertia of a solid sphere when the axis, the rotating axis passes through the center of the sphere. Okay, right? This is basically how this is defined. We basically first derive the half mr squared for a cylinder or a disk, and then we utilize that in the next for the derivation of the moment of inertia of a solid sphere. Okay. So here are a couple other examples. If you have a rod, then it will be 1/12 of ml squared. L is the length. And if you move that axis to one end of it, that's 1/3 of ml squared, right? So here's another case to show you, all right? And for the same object, when you move the rotating axis, rotational axis, the moment of inertia actually changes, right? So this is for a slab, for different types of cylinder, hollow cylinders, for spheres and very thin wall hollow spheres, that will be 2/3 of my mr squared, okay? Right, so now I'm going to introduce a theorem that's called parallel axis theorem. And basically, using this theorem, it will give you the relation between the moment of inertia of a body about an axis through it, the center of mass, and the moment of inertia about another axis here that's parallel to the axis that pass through the center of mass, okay? To the original axis that pass through the center of mass. So what this theorem tells you is for the newly defined axis, the moment of inertia is equal to the moment of inertia of this axis that passes through the original axis that passes through the center of mass, plus the total mass of this object times d squared. D will be the distance from the new axis to the original axis that passes through the center of mass. Let's together derive this parallel axis theorem, right? Here is our setup. We basically have a rigid body, right? And we have axis C that passes through the center of mass point, C here, and here now we move this axis up by distance d, here by distance d, away from the original axis. And now we say that the moment of inertia about the original c-axis is IC. And let's start working out what the new moment of inertia around the axis L would be. So we're basically summing over all of the little masses here. We can use sum, we can use actually, integration here. It doesn't matter. And basically have this little mass times the distance, the new distance from the distance of this little mass from the new axis L, that will be the old distance minus d, right? So this whole thing here is r, and then it moves up d, that's r minus d, okay? Right, so we expand this term, right? And then we arrive that the moment of inertia has 3 terms, right? The first term is basically the moment of inertia about the c-axis. The third term is actually is here. This one will be the total mass, right? And what is the second term, right? Okay, the second term, because the origin C is the center of the mass, then the sigma or the sub overall over R would actually equal to 0, right? This is basically the definition of a center of mass, right? So that's why this term actually cancels out. It's actually a 0 term, and then your angular, your moment of inertia is basically the moment of inertia of the original axis that passes through the center of mass plus the distance between the two axes raised by the second power times the total mass. Okay, so basically now we've derived the parallel axis theorem. Okay, right. So we can use this to actually calculate, for example, the thin rod case for the the thin rod. If we have the axis that pass through the center of map, which basically is the center point in this rod here, is a moment of inertia is 1/12 of ml squared. What if we move it to the end, right? We move it by d, that is equal to L divided by 2, right? Okay, then the center of mass around this new axis will be the original IC, right? Plus m times d squared, right? And the d will be the L divided by 2 here, right? And then we pull the ml squared out. That's 1/12 plus 1/4, and that's 1/3 of ml squared. This is where you can actually use parallel axis theorem to actually derive the momentum inertia when you are moving and the rotating axis around away from its center of mass. So for any of these objects, it's always very useful to calculate what the moment of inertia is when the axis pass through the center of mass. And then when you move it around, you basically simply using the parallel axis theorem to give you the new answer rather than actually redo the integration. Okay, so here's a little chart of all these different shapes of rigid body and what their moment of inertia is. This is a very good reference place. You can actually look up all these moment inertia formula for a certain given shape of rigid body. Okay, so now we've basically in this class covered rotation, the speed of rotation, the velocity of rotation, that is basically the angular velocity. We talked about angular acceleration. We talked about it's how the rotational angle is connected to the angular acceleration when we have a constant accurate acceleration, angular acceleration case. We talk about how the kinetic energy is connected with the moment of inertia, and also we've talked about how to actually calculate these moment of inertia. Okay, so now class is finished. Class is dismissed.